Here we are again. Hopefully it's going to stabilize and show. Now let me just adjust a little bit like that. Hope you can see. Okay, fine. Assalamu alaikum once again. I'm back for the next lecture, and this is where we reached. Okay, so I will not, since you know we did this last example. Now we want to go straight away to the roots of complex numbers. So we'll think of roots of w, a complex number, and then w power n equals z, which is another complex number. By the way, that always happens because complex numbers are algebraically closed. So that means that we'll always get, the roots inside there. We solve equations here and they will always have solutions. It's not like for real number cases. Okay? So, proposition. A complex number w in C is the nth root of another complex number. If this is the nth root, that means that if you raise this to power n, you get z. Or nth root means that w equals, you raise nth root of z. Okay? If w, remember, any complex number can be expressed in polar form. So if this is a polar form of w, that means w is rho, which is the radius, cos phi plus I sin phi. And the polar form of z is r cos theta plus s sin theta. Then, using this, we can just say that w to n equals z is the same as, you raise this to power n. And then here we've done that. Power n of this, by De Moivre's theorem, will give you cos n phi plus I sin n phi. And this equals z, which is r cos theta plus I sin theta. Which means now we can just equate. We just equate that rho n equals r, n, or if you take the nth root of rho, you just get, r to the n. R power 1 over n. Likewise, we can equate this. Now, this equals this, and so this equals this, and this equals that. That means that cos n phi equals cos theta, and sin n phi equals sin theta. That means now the angle is basically, so n phi, remember our theta is periodic, so we can say our theta is 2 pi k. So, to get now, you just ignore this and this. You can just say, this equals this means that n theta, or n phi equals theta, but theta is periodic, so it's just saying that phi will be theta over n, but our theta is periodic, so phi is theta plus 2 pi k over n, where k is an integer, 0, plus or minus 1, plus or minus 2, plus or minus 3, and so forth and so on. And thus, the nth, well actually the n is supposed to be the nth roots, because there are n of them. Nth roots of z are given by wk, so you raise this to power this r, the nth root of r, this is the nth root of r. Then this angle theta, we already said is given by this, so it's just theta plus 2 pi k over n, plus I sine theta plus 2k pi or pi k over n. This gives you the nth roots. Whenever you're given a complex number in this form, then to get the nth roots, all you do is you just apply this, ladies and gentlemen. That's what I've just explained. And then here I have a remark that just says that geometrically, the n roots span a regular n-gon. What am I saying really? If the roots are 2, then they just span, think of them like, once you get one root like this, what do? The other root will just be 180 degrees to the other side. That's just a line. If the roots are 3, then once you find the first root, then you just measure 60 degrees, you get the other root, 60 degrees, the second root, and 60 degrees you go back. So basically it spans an equilateral triangle. That's what we're calling a regular n-gon. If the roots are 4, it's going to be a square. If the roots are 5, it's going to be a pentagon. If the roots are 6, it's going to be a hexagon, and so forth and so on. So basically this geometric way is easy for you. Once you find the first root, then you just need to divide 360 degrees by n, then you get how many degrees you need to keep measuring to get to the next angle, root. Okay? I hope it makes sense. So let's look at an example. So example number 4. Find the three cube roots of z equals I. Now remember, we need this in polar form. And this in polar form means that we need our radius. So x is 0, the real part of this is 0. The imaginary part is 1, so our radius will be 0 squared plus 1 squared, square root will just be 1. And then the argument of I is pi over 2. We already saw that. I can show you again if you want. So the 3 cube roots will be given by, so all you do is you apply this formula. You just need to remember this formula. So our radius is 1, so it's 1 to power 1 over 3, which is what we have here. And then here you have theta, but our theta is the argument of z, which is pi over 2. And then 2 pi k, sorry, I'm confused here. So this is pi over 2, then 2 pi k over n is 3. So you just have the 3 cube roots will be, well, it's just this is just 1. Cos pi over 2 plus 2k pi over 3. This is making noise. Sorry, there's been an echo. I hope now sounds it better. Over 3 plus I sine pi over 2 plus 2 pi k over 3. K is 0, 1, 2. There are 3 roots. So when k is 0, the first root will be w0 will be, you put 0 here, this disappears. You have pi over 2 divided by 3. It's pi over 2 times a third, which is pi over 6. So it's cos pi over 6 plus I sine pi over 6. Now, pi over 6 is, pi is 180 divided by 6 is 30. So cosine of 30 is normally root 3 over 2. And the sine of 30 is a half. And this is actually the principal third root or cube root. Okay, here I'm supposed to say cube root. The principal cube root of this number, complex number, which corresponds to the argument, because the argument, the principal argument is pi over 2. Then the other roots, when k is 1, we put 1 here, you have pi over 2, then this is 2 pi over 3. So pi over 2 plus 2 pi, this would give you 2.5 pi over 2, and then divide by 3, which is the same as 5 pi over 6. I mean, this comes down here. So this is 5 pi over 6, I said 5 pi over 6. Well, this is the same as root 3 over 2, I over 2. You can check that. And then when k is 2, then you put 2 here, you have 4. So it's pi over 2 plus 4, this is 4.5 over 3. If you multiply by 2, it becomes 9 over 6. 9 over 6 is the same as 3 over 2. So it's 3 over 2 pi plus I sine 3 pi over 2. And anyway now, well, what is 3 pi over 2? Wait, pi over 2 is 90 degrees. 3 pi is 270. 270 goes like this. You have, okay, look at it this way. Let me take you back. Sorry to take you back like this. I mean, if I'm here, 90 degrees, if I measure 90 degrees, I have 90, then 180, then 270. 270 goes down here. Down here corresponds to I, or rather minus I. So that's why, now where are we? Sorry, I've actually taken you back very far. It turns out to be minus I. I hope it's clear. Eh? That's the end of that example. Next is example number 5. Find the fourth roots of z equals 1 plus I. So we have, well, x is 1, y is 1. So r is the square root of 2. 1 squared plus 2, 1 squared, square root is the square root of 2. And then the argument of this is when now tan inverse of 1. 1 is where cosine and sine are equal. It's just pi over 4, 45 degrees. Okay. So the fourth root will just be the same formula we had. Our radius is this. You find the fourth root of that. Then cos of the argument pi over 4 plus 2k pi over 4 plus I sine the same angle. And then there are 4 roots. So it's 0, 1, 2, 3. So you just vary the values. When k is 0, you put 0 here. You get pi over 4 over 4 is pi over 16. Pi over 16. Then you can use your calculator. You can compute that. When k is 1, you have here, this is 1, so it's just 2 pi. So this is 2 pi plus pi over 4. This turns out to be 9 pi over 16, which you can calculate. Then when k is 2, you put 2 here, you get 4 pi plus pi over 4 over 4. This will give you 17 pi over 16, which again, you plug in your calculator, you get that value. And finally, when k is 3, you put 3 here, you get 6 plus pi over 4, 6 pi plus pi over 4. It turns out to be 25 pi over 16, which again, you can compute to your calculator there. And that's that, ladies and gentlemen. That's the end of roots. Next section is actually about, what are they called? Sets in C. Now, this one, I wonder whether we should stop here or we should go to the next. It doesn't have much, but maybe I should give you when you're fresh. Are you fresh? Okay, let me say something. So, in the complex plane, you do have sets. Now, the first thing we say is that, well, we have several definitions. So the first definition is every neighborhood of Z contains at least one point in S. Hey, wait. Now, I've started in the wrong place. This is where I'm supposed to start. The first definition for section 17.3 talks about, so suppose you have a complex, you have a fixed point, complex number. Z naught equals the real part, imaginary part. And then you have Z equals X plus IY. Then you can talk of distance. The distance between these 2 points is simply, you just take the real part minus the real part squared, the imaginary part squared. That gives you the distance between these 2 points. The equation, this equation, here we're calling it rho, that distance, okay? And that's our radius. So this actually represents the equation of a circle of radius rho with center Z naught. Actually, think about it, it's a circle because this, if you look at this one only, equals rho. If you square, the square root disappears. So you have this squared plus this squared equals rho squared, which is the equation of a circle whose center is X naught, Y naught, and radius is rho. This is exactly what we're saying there. That's the first definition there. Okay? So that's a circle. So we always represent a circle this way in the complex plane. Then for all Z in C satisfying the modulus of Z minus Z naught is less than rho, then such Z is in the neighborhood of Z naught. That means it is near Z naught and does not pass rho this length. We can think of the set S, complex numbers, such that they satisfy that. We can think of this as an open disk. Anyway, ladies and gentlemen, I think I want to stop here. Then I can come back in the next video. Why? Because I think maybe you need to be fresh for the next one. Okay, so we'll continue from there.